have a link. So in fact, yeah, I'll share the link later on. So I mean, data pre-processing, it's very important, but maybe it's not very important today. In fact, when you are working with deep learning models, because the idea here is to which activation function we will use. So for some activation, for some activation function, we don't care about this data pre-processing. But anyway, it's also useful because I saw also some recent papers, people try to work with this explainable AI, and they try to select, in fact, simple models. Not all people need to go for, deep learning models, but some people also try to use those, random forest and stuff like this. So maybe also it's important to look into data pre-processing. So first, I need to talk quickly about this inseparable data sets. We talked about it last time. So when a data set is linearly separable, it means it is possible to use maybe a straight line or a model which will generate a decision boundary, which is a straight line which can be used for, separating those two, maybe two classes or more, for example. So in this case, we can use a linear model. But if your data set if your data set has higher dimensionality, for example, and it's not possible to use, and it's overlapped, and it's not possible to use a linear model to separate those data lines. So in those two classes, for example, so in this case, we need to work a little bit with the data and try to make it separable, for example. So I have here some very simple problem. This XOR problem. It's very simple. This is a truth table. So the input features, it will be 0, 1, 0, 1, 0, 0, 1, 1, and the output, it will be 0, 1, 1, 0. So it will be 0 when both inputs are similar, and it will be 1 when it's different. So it will be like this one. So it's 1 when it's different. So when you plot it in XY coordinates into dimensional space, we will have like this blue and red. And if you need to separate it, in fact, those are two classes. So we need a model which can make something like this one. We need a model to make it like this one. So all data points which are between the two lines, it will be classified as 1. All data points which are outside, it will be classified as 0, for example. So it's inseparable, in fact, right? Because we have two classes, so it's a binary classification problem, but it's impossible to use one model or one straight line to classify it. So if I selected maybe one line will be like this one. So in this case, it will be like accuracy will be 50%, because maybe this one will be correctly classified. This one will be, maybe this one will be wrongly classified. This one will be wrongly classified. This one will be correctly classified. So it's impossible to achieve this using a linear model. So if you want to use multi-layer perceptron classifier for this simple example, we just need to build our data set. So this is inputs. This one will be the labels. And we will use MLB classifier. MLB classifier, it's feed-forward neural network. You can use any activation function. You select a number of iterations. This is a number of hidden layers. How many hidden layers and how many neurons in each hidden layer? So when I select it like this one, it means we have only one hidden layer. A number of neurons in this hidden layer is 2. And of course, my input, you don't need to define inputs and outputs. It will come automatically from the data. So when you look into this line and my data, you can say that, okay, this model will consist of one hidden layer, and this hidden layer has 2 neurons. And when we look into our data, we have only one label, one column. So in this case, the output layer will consist of 1. And for the input, we have only 2 inputs. So which means it will be like this one. This is the input layer, which consists of receives x1 and x2, or x and y, for example. Sorry, x1 and x2, yes. And it will be like this one. So it will be a model like this one. So in this case, it will be very simple. So this is feed-forward neural network, and it's very simple because we need to use it for classifying XOR data sets. We will train the model using x and y, and after that we will just predict, using x and predict labels for all x, and we can print model coefficient, and we can calculate error right? Precision error. And we can plot confusion matrix. It's very important to plot confusion matrix for classification problems. For regression, you don't need to do this. We use this confusion matrix only for classification problems. And if you want to plot the decision line, because this is multi-layer perceptron or feed-forward neural network, so it's difficult, in fact, to create a decision line like an equation, right? So in this case, it's better to use this mesh grid approach and try to generate XY and X1 and X2, for example, use mesh grid and send all those points to the model and predict YG. And after that, you use contour plot or something to plot your output. So it will be like this one, right? So, okay, we don't have it. So it will be like this one. It will generate those two lines here, right? This model is very simple. So in reality, your model here, I mean, this one will generate one line, this one will generate another line, and this one will combine the decision. So because this is simple model, so we will get this decision line. So we will get two lines, and all data points between the two lines will be classified into +1, and all data points outside it will be classified into 0, for example. So it will be like this one. So yes. So if you want to make it more complex, you can make this XOR more complex. So just to generate more complex data sets, as you can see here, this one it's like +1, +1, this one 0 and 0, but it's kind of overlapping. And in this case, if you will use the same model, you will generate straight lines, so the accuracy will not be 100%. So in this case, maybe you need to make your model a little bit more complex. So you can make your model a little bit more complex by maybe adding more neurons to the hidden layer. Just add more neurons to the hidden layer. As you can see here, my hidden layer now has 20 neurons, so it will be more complex. When it is more complex, it will just generate more complex decision boundary. As you can see, it's more complex. And just to be sure that it will not overfit, you need to ensure that it will not overfit. If you will run your model several times, each time you will get maybe different results. So if you don't use random seed, and when you run your model each time you will get different decision boundary. So we understand it, because each time we will initialize our weights with different set of random values, and you will use your solver, right? This is my optimizer. When we use this optimizer each time, we will update the weights, and we will end up with a different model. So we understand it. If you don't want to end up with different model each time, in this case, we need to use random seed. So we can initialize the weights with the same set of values, and we can reproduce our results. So this is very, very important. And at the end, because this is classification problem, we will plot the confusion matrix. And also you need to get maybe this classification report. It's very, very important to get your classification report. So now it's just an introduction to data preprocessing, the importance of data preprocessing. If you have this XOR, which is complex to solve, maybe we can try to simplify it. If we can try to invent a feature, higher order feature, which can consider interactions between my original set of features. It's just if you can play. So if you will train your model with X1 and X2, this is X1 and X2. In this case, you need to have a complex model, and this complex model, similar to the one which we just show here, it has 20 neurons in the hidden layer, so it's complex model, and it has large number of weights. But if you want to simplify it, you need to work a little bit with your features. So for example, instead of training my model with X1, I can train my model with X1 and X1 times X2, right? So just make small changes, right? It requires, of course, time, because you need to maybe trial and error, but just it's just as an example. If you will train your model with X1 and X1 times X2, in this case, you can see here in this figure, you can just use a perceptron. You can use a perceptron to classify the same data set. So this model here, it requires a very complex model, feed-forward neural network, which might overfit. But when you play with your data set, and instead of using X1 and X2, which are my original features, in this case, I will use just X1 and X1 times X2. So we will invent a new feature, and this feature will consider interaction between between features. So it will be multiplications. It will be linear combinations, or it will be a combinations of my feature set. So for example, I will test x1 times x2. Maybe someone else, he will consider x1 square and x2 square and so on. So now if I will use x1 and x1 times x2, the data set will look like this one. And as you can see now, I can just classify it using a simple perceptron. This one will be generated by a perceptron, and it will give me the same results, right? We will get accuracy of 100%. Maybe the results will be much better because this model is simple and it's easy to explain. People who are working in explainable AI, they want to explain how, which features has more impact and how the model will make decision. So now it's easy. If we can simplify our models, it will be easy for people to understand how the model is constructed and how the model will make decisions. Maybe you can use this classification. It's binary classification, but binary classification problems are very important because you can work on a sequence of genes, for example, chromosomes, and we need to classify if the person will develop, for example, a kind of disease, for example. I'm working on a data set with a professor from University of Oslo, and we use those sequential chromosomes for predicting if a person will be able to develop maybe obese in the future, right? Metabolic state prediction in the future, for example. So it's a binary classification problem. So why should we go for complex models if we can solve it using simple one? But if you need to do this, you need to look into your input features and try to work a little bit with it and try to find a combination which will make your data set simpler. So now I'm plotting my data, as you can see here, x1 against x1 times x2. When we are plotting x1 against x1 times x2, as you can see here, the data set become very, very simple. We have one class above, one class below, and it's easy to just use a perceptron to classify it. So my classification will be very, very simple. So here, in fact, I used x1 and x1 times x2, and now we trained a perceptron, right? This is my perceptron. And at the end, we can print the coefficient and the bias, the y-intercept. So we will have omega 1, omega 2. So my model will be like this one. It will be omega 1 times x1 plus omega 2 times, in fact, x1 times x2 plus p equals 0. This one will be my model. This one will be my decision line, right? So if you want to plot your decision line, so generate values for x1 and substitute, those values for this one, and plot your decision line against x1 times, but just to call x1 times x2, call it maybe x3, for example, to make it simple. So this one will be omega 1 x1 plus omega 2 x3 plus p equals 0. Generate values for x1 and plot x3. So x3 will be minus omega 1 divided by x2 by omega 2 times x1 minus b divided by omega 2. It will be like this one. So now we can, and in fact, if you want to plot this one, it would be beautiful, in fact, if you can reverse this one into this one to see how the decision boundary will look like. I know x3 is x1 times x2. We have x1, so I need to get x2. So x2, in fact, will be x3 divided by x1. Try to do it like this. And try to visualize this decision boundary in the original plane, x1 against x2, to see how it will look like. It will be very beautiful. So, we did also this problem last time. Those make circles. It's a data set from sklearn data sets. It's a simple function, and you can just you can generate those two circles. And as you can see, those two circles are inside each other, and we need to classify it. So classifying it is difficult because I need to generate a decision boundary, which will be a circle in the middle here. So simple. So instead of using x1 and x2, in this case, I need to really have very complex maybe model. So instead of working with x1 against x2, I can train my model with x1 square and x2 square, for example. So in this case, we can use a perceptron, and this perceptron will generate this complex circle, right? So in fact, it was very, very simple model, and but because we have been working with this feature engineering, we call it feature engineering, and you can train the model using a super feature. This super feature will be, instead of training your model using x1 and x2, just to train your model using x1 square and x2 square, for example. So in this case, your model will be very, very simple. And you can just invent. You can use genetic programming. In fact, genetic programming can be used for constructing more complex equations. Genetic programming is used for generating equation. So the input to my model will be like x1 and x2 and some operations. Those operations, it could be multiplication, it could be square root, it could be sine, it could be cosine, and you can just try to create a super feature, and this super feature will simplify your model. It will help you to convert your data from inseparable into separable. Yes. SGD classifier, I mean, we don't need to talk about this, in fact, because this SGD classifier, I want to go into, maybe it's just support vector machine and stuff like this. How can we use SGD classifier for MNIST dataset? I mean, it's simple. Yeah, but we can talk about it. SGD classifier, in fact, it's designed to to be efficient for large scale and sparse machine learning problems which cannot fit in memory. The classifier optimizes different loss function for classification by using stochastic gradient descent. And stochastic means, of course, we did that last time. It's online training. We just train my example by example. And it's linear classifier, which is support vector machine logistic regression with SGD training that is used for binary classification problems. And also you can train it for k-separable binary classes. And it can also use the technique which is one versus all or one versus rest approach. So I will just skip that part. Yes. So we need to talk about feature selection. Feature selection. If you have 10 features, for example, how can we select the most important subset of features? Feature selection, we use it for dimensionality reduction. So the importance of feature selection can be, can be recognized when you are dealing with data set which contains large number of features. So you have large set of features, and you need to select the most important features which are relevant to my problem. So this type of data set is referred to as high dimensional data set. It's high dimensional. You have very large, you have a data set, and this data set contains high set of features. So we need to reduce the set of features. We need to select the most relevant features for my problem. And it's important also for explainability. So I can train my model. Someone can train his model with 20 features, and someone can train his model with 5, right? Which one will be easy for us to understand? Of course, the one with 5. So in this case, we need to learn methods which can help us to select the most maybe relevant set of features, for example. So with high dimensionality, it comes a lot of problems such as increase the training time and the cost. Of course, I need to train my model with 10 or 20 features, so it will take time and it requires computational power. And also my model will be complicated, and also it might lead to overfitting. Your model will be complex, so it will be very difficult to explain. People who want to work with explainable AI, it will be difficult because I have a larger set of features. So don't know which feature has more impact compared to the rest of the features. And also chances to overfit, it will be very high because when you have large set of input features, you need to build a complex model. So number of parameters will increase. And in this case, the chances to overfit will be very, very high. In addition to that, of course, the time, training time, and the cost. So in higher dimensional feature set, there might be also several features which are redundant sometimes, which means that these features are nothing but extensions or combinations of other essential features. Sometimes you have 10 features, but not all those features are important because there are some redundant features. Some features are a function of other features. So it will not carry new information to our model. And in this case, it will be important to try to lower dimensionality and select the most important set of features for your problem. So these redundant features don't effectively contribute to the model training, and therefore there is a need to extract the most important and most relevant features from your data set in order to get the most effective predictive model. So we don't need to work with some features which does not carry in new information to my model, right? And of course, also there are some trade-off because when we reduce the dimension, maybe we will lose some information. I mean, there are some features which are a combination of other features, but also maybe there are some features which might maybe carry 5% or maybe 1%, 2%. So we will lose some information when we do this feature extraction or feature selection, for example, or dimensionality reduction. But at the end, my model will be simpler, and it will be easy to explain my model to people and communicate my results with other people. Because, for example, if you are building a model for maybe for medical application, it's very important to explain, I mean, why you are using this feature and which feature has more information and relevant to my decision making. Because also data collection is complex. In fact, when you are collecting data, it's complex and it requires a consent from the patient and his family. So do we really need to collect this one? Is it really important for my problem? So it's very, very important to decide in advance which features you want to use. So feature selection, it enables the machine learning algorithm to train faster. It will train faster. It will reduces the complexity of the model and it will make it easier to explain. So it's very good for interpretability and explainability. It will improve also accuracy of the model if the right subset is because sometimes you will use more features and those features it might make your model confused, right? So it will be very difficult. I mean, it will not have maybe sometimes positive impact. It might have also some negative impact on your model accuracy, for example. And of course, when we work with small set of features, it will reduces the chances to overfit. It's just because the model will be simpler. So your model will be simpler. If you have small set of data, and if you will use larger set of features, in this case, your model will be complex. You don't have enough data points or samples to train your model, so chances to overfit will be very, very high. So there is very nice function in Python. In fact, there are many techniques, but we will just talk about this function. It's called select k-best. Select k-best, and it's a feature selection, and it's based on a statistical test. So in fact, you need to select. There are lots of also statistical tests which you can use. For example, you can use this one. You can use many other things, in fact, and it will try to remove all but the k highest scoring features. So here, in fact, we have hyperparameter, and this hyperparameter is k. If you have 10, for example, you can say, I need to select the most important five best features, for example. So the most, relevant 5 features based on this statistical test, for example. So you can reduce or chi-square, for example. So it will help you. It will help you to reduce the set of features. So if you have 10, if you have 20, you can say, I need to train my model with 5, check accuracy. If you need to test with 7, with 8, with 9. So it will be nice, in fact, if we can build the machine learning pipeline and use grid search. And in this grid search, we will define values for k. I need to test k for maybe 5, 7, 9, 12. And each time you will calculate the accuracy. And using this grid search, it will help you to select or to optimize this one. What is the best value for k? So if you want to use this approach, you need to use it. It's in fact select k-best. We need to import it from feature selection, sklearn.feature selection, and you need to select the statistical test, for example. And here, for example, I will just test it with this iris dataset. Iris dataset, it's simple. It has only 4 features, right? So iris dataset, it has only 4 features. So what will happen if we need to select the most important 2, for example, from those 4? But if your problem is large, you will see that it's beneficial when you have a large set of features. So now we need to select the most important 2 features from iris dataset, for example. So you just need to maybe define a selector, for example. It will be select k-best. You need to decide what is the statistical test which will be used for sorting it, because we will get a score and we will sort it based on this score. and we will select the highest two scores or the highest two features with the highest, maybe this correlation coefficient or something. So in this case, we will get X new. So my original features were X, and now we will get X new or X reduced, for example, by fitting this selector with my data. It will calculate correlation between X and Y, and it will give you scores, and it will sort it in descending order, and it will select the highest two. So this is the whole task. So now we will get, if you want to see the score, so those are the whole scores for the four features. We have only four features. So the score of X1 was 10.8. The second one was 3.7. The third was 116.3, for example. And the fourth one was 67.04, for example. So when we are sorting it, it is clear that this one, it is the highest, first highest. This one, it is the second highest, right? So in this case, we have X1, X2, X3, X4. So now we will just select X3 and X4 as my subset or reduce the set of features. So now we will select those two. So which is X3 and X4. Now I can train my model using only X3 and X4 without losing too much information, right? So if you want to select a subset of features, you can just use select k-best. I mean, the advantage of using select k-best is that it will return the score, and the output will have a meaning, because now we have X3 and X4, and we know what is X3 and X4. It was beta length and width, I guess, or Sybil length and width. So which means those two features are more relevant for my classification problem. And maybe it's not very important to use X1 and X2. If you want to select 3, it's fine. In this case, you will use X3, X4, and X1, right? So now we are selecting based on statistical test. So we have some justification, right? We have a justification. So in fact, X3 and X4, it's beta length and beta width. So beta length and beta width are more relevant, in fact, for my classification problem. So in this case, we don't need to classify this problem using 4 input features. We can just select 2 input features. And in this case, we will reduce dimensionality. And then when we reduce dimensionality, it will be easy, in fact, for plotting. So because this problem, we have 4 input features. So if I need to plot it, maybe maximum, I can plot it in 3-dimensional space. But in fact, so I can just select X3, maybe X4, and X1, right? Based on this. So because we will skip X2, because X2 has the lowest score. So in this case, I can plot it against X3, X4, and X1. Or if you want to plot it in 2-dimensional space, I can just select X3 and X4. And now it will be, it will be much better for us to visualize my classes against X3 and X4. And I can train my model using X3 and X4, or at most X3, X4, and X1, for example. So this select k-best is very nice technique. If you are, writing a paper, for example, you can just try to use select k-best and check your results. It might better than, or just, it's just results, right? We try to simplify. And after that, you can talk about explainable AI and how can we explain our results in terms of our features. So there is another. So this technique is very nice and it's beautiful and it's easy and it's based on this statistical test, for example. And there are many approaches here. You can use this function. You can use chi-square. There are many approaches, right? So each time maybe you will get it will not be very different, in fact. But you can test also different statistical test. So now we will talk about principal component analysis. Principal component analysis also, we use it for feature for dimensionality reduction, and it's unsupervised technique, and it's used for simplifications and data reduction or compression. So if you want to compress your data, we can use principal component analysis. If you want to reduce the dimension of your data, we can use principal component analysis. So the input to this principal component analysis, it will be your set of features, and the output will be principal components. So it's in the same way. I will test it here with MNIST, because MNIST dataset has each image has 28 times 28 pixel values, which is 784 pixel values, and I need to simplify it because not all pixels are important for us, right? Because usually for this handwritten digits, so people usually write in the middle here, correct? So most of the space, in fact, it's zeros. I mean, it's not important. Most of the space is just does not carry any information. So in this case, I will use principal component analysis because I want to find the most important principal components which can be used to build a model or a classifier. So I don't need to use the whole image because now we are working on pixel values. We use feed-forward neural network, and we will feed all those input pixels to my model. So my model will have 784 inputs. So it will be very, very large. So one way for simplifying it is to use principal component analysis, for example. So a principal component, if you want to use it, you need to use it to import it from sklearn.decomposition, PCA. You need to get principal component analysis. Principal component analysis, it has one hyperparameter called n components. So this n components, it is a number of components which we want to select. Number of principal components which we need to get. So you can say, okay, I need to get maybe 64. This is image. So I just selected number like 8 times 8 because I want to reconstruct this image one more time and put it and try to display it as an image. So I'm just selecting 8 times 8, but of course you are free to select any numbers. So now I need to compress the image from 28 times 28 to 8 times 8. So it's compression, in fact, correct? It's data compression. And we need to see if we will lose any information or not. I mean, after doing this compression, are we still able to read the digit? Is it still, if this one was 7, is it still 7? Can we read it? Can we recognize it after this data compression? So we will use principal component analysis. We need to select a number of components, number of principal components. So it will be 8 times 8. We will fit x, only x, to this model and therefore it's unsupervised, right? This approach, it's unsupervised. If you can go back to select k-based, no, it's not unsupervised, it's supervised, in fact, because we are feeding x and y to this approach, x and y, because in fact it's based on a statistical test, and we try to calculate a correlation between x and y, and we will get the score, and based on this score, we will select the most influential, most relevant features. But in case of principal component analysis, no, it's unsupervised. It's unsupervised. So we will feed it only with x, not x and y, only x. And we will get from this one x reduced, right? So the input will be x, and the output will be the reduced set, x reduced. And also, in fact, you can get also, it has also principal component to explain the variance. If you want to see the explained variance, how much information is explained by each principal component, we can get this explained variance ratio. Because the input to this model will be x, and the output will be x, will be principal components, right? Principal components. And I need to see how much information is carried by each principal component. It will be also sorted. So maybe the first principal component, it will carry maybe 50% of the information. The second principal component, maybe it will carry also maybe 15%. Maybe the third will be like 10%. Fourth will be maybe 7%, and so on. So if you want to see the explained variance, this explained variance ratio, it will give you how much variance or how much information is carried by each principal component. You can plot this cumulative sum. So if you want to plot it like this one, so I can have on an x axis the principal component 1, 2, 3, 4, and so on, and how much information is explained by each principal component, and we can plot a curve, right? So you can say that this curve will go from maybe from 10% to maybe 100%. And from by looking into this curve, you can just say, okay, now I will use maybe the first 5 principal components, because the first 5 principal components, maybe they carry 95% of the information or the variance. So we don't need to use the whole set of principal components, because if I will use the whole set, there will be no advantage for us. Yes, please, Axel.
Yeah, I just wonder these principal components are those the features in the data set? Is that how you
The input is
uh,
the features, but the output is the principal components, not features. The output does not have any physical meaning. So the input here will be pixel values, but the output will be principal components, and those principal components does not have any physical meaning. So, for example, if we have a data set and the input, I mean, my features are age, education, for example, correct? Maybe blood pressure, income, and so on. And if you will use principal component to create those principal components does not have any physical meaning. So you cannot say that the first principal component is age. No, it's not age. It's not anything. It's something statistical, in fact. I mean, the principal components, there are like new features which are perpendicular to each other. It's something statistical. So
uh,
I had some explanation of yes, Ihtisam, maybe you can explain it.
Yeah, actually, I have worked with principal component analysis. So, as far as I am concerned, I guess these are used to present the low representation for high dimensional data. For example, in terms of image analysis, they are used to compress the images, and the applications are like zip files or RAR files, something like this. So this low dimensionality using PCA doesn't reduce the compromise the quality of the image,
Mhm.
but the performance is almost the similar. So these are the features that are used to give us the less dense representation in low dimensional space. Yeah.
Yes, this is correct. So we represent our data in lower dimensional space.
but
But
just in a concrete example, if you say you have this age, gender, and whatever features,
mhm,
and you say you have a principal components 1 to 4, and you say, okay, we will only use the 4 first principal components. What will then your sort of your training set be? Is it just a reduced set of
yes,
the original one, or
this is correct. We call it principal components. But those I mean, the first principal component, it will carry some information about my variations. In fact, it's called variance. It will just explain some variance. So, for example, if you have a data set like this one, imagine it's like this one. We have here x1 and x2, and we have some data sets like this one. So maybe the first principal component will be this line, which because this we will select this one as the principal component because this one will explain too much variation in that direction. The second principal component, it will be perpendicular to this one, and it will carry less information because the variation in the second direction is much less. It could be XY, maybe your data set will be in three-dimensional space, right? It will be like this one, so distributed like this one. So we will select the first principal component, which will explain too much variation, the maximum variation. So maybe in that direction, we need to have the first principal component in that direction. And the second principal component, it will be perpendicular to this one. The third also will be like, so it's like mapping the coordinates into the direction which has the largest variance.
and these are all
So
just statistical approaches compared
yes,
to the last one that was sort of the relation to the uh,
in fact, if the input is three features, the output also will be three principal components, three components. It will be the
mm,
same number, but we just change the orientation to explain more variance, right? So we will just, it's like a mapping, create mapping between inputs and outputs. So number of inputs will be three, number of outputs also will be three. But in fact, because the principal components are perpendicular to each other, so in this case, maybe the first principal component, it's the one which has lots of variance or in the direction of most of the variance on your data set. The second will be the second most. The third will be the third most. So in this case, I can select maybe the first two will be enough because they will carry I mean, they will explain most of the variation in my data set. I don't need to select the third, but you are free to select the third, correct? So in this principal component, in fact, number of outputs will equal to the number of inputs, but it will be sorted in descending order using this variance or explained variance, for example. And you can just, if you want to make reduction, for example, I can just say, okay, I will select the most, the first five, most five or six, for example, out of 10. So in this case, we will reduce the dimension of my data. So instead of plotting my data set in 10, if it is in 10, if I have 10 features, right? So I can just select 5, and I can say, okay, now I will go with 5 because 5 is enough. Those 5 carry most of the information in my data set, and it's enough to use 5. The most.
For example, just to get a picture of it. So say that you have a picture and you use the principal component analysis, and then it was said that it was just a compression. Then you will actually be a visible picture afterwards, right? It's sort of.
Yes, I mean, yeah, of course, but it could. Yeah. I can just try to write here principal component analysis. PCA.
Yeah, I can Google it myself also, but
yeah,
I want to.
I want to find a figure. It's like this one, for example. Do you see this? Yeah. So it's like this one. You have a data set, and this data set is represented by, the feature, it's x0, x1, and x2, and it has any kind of distribution, for example. So as you can see here, we will select maybe the principal component. It's the first component will be the one which has lots of variations in that direction, for example. So maybe it could be, for example, the blue one, right? So we will select, I cannot draw here. So the second one will be perpendicular, and it will explain a little bit less than the blue one. And the third one, which is the green one, it will explain much less because there is not too much variation in the green direction, as you can see here. So there are lots of variation in the direction of the blue one. So maybe the blue one will be the principal component. Maybe the second principal component, it will be the red one. And the third will be the green one, right? I can explain this one later on. I had, in fact, some slides where I had lots of details, but I removed it because some people, found it's not very important. So, but as you can see here, the input to the principal component are 3 features, which are x0, x1, and x2. And the output from the principal component also 3 components, blue, red, and green, right? So you will look into your data, you can see, okay, I have lots of variations, in fact, or in the blue direction, and the second most in the red direction, but the green is not very important, right? So I will just ignore the green one. So now I can go with the blue and red. Maybe blue and red, it will carry maybe 80% of the variations or the variance in my data set. So we can say that, okay, now I will simplify my data and I will train my model using the blue and the red. But do you have any meaning for blue and red? No, it does not have any physical meaning. In my original data set, maybe x0, x1, and x2, it's pixel value, which has a meaning. But green, blue, and green, red, and the blue does not have any meaning. You cannot say that it's pixel value. No, it's not.
Thanks for the explanation.
So maybe I will try to make it so just step by step. So now this principal component, okay. So just we need to agree that the principal component is the input, maybe will be n features. The output will be n principal components, right? But those principal components, they will be perpendicular to each other, and each principal component will explain some variation of my data. It will carry some information in my data set, and it will be sorted from high to low, and you can just select maybe the most, maybe the first principle, the second, the third, fourth most, and so on. So anyway, as you can see here, we have something here called the cumulative sum, and this one, in fact, it will just, it's the addition of, or cumulative sum of the explained variance of each principal component. We can print it out, we can plot it, and after that, I will feed X to my my model, and we will get the X reduced. The X reduced, in fact, it will be based on the number of n components which you decided. So if you want to make reduction from 28 times 28 to 8 times 8, for example, because I need to reconstruct the image, right? So I will make reduction from 28 times 28 to 8 times 8 using the most influential 64 principal components, and we will reconstruct the image, and we will see how the image will look like. So now do you see here? We have this fit transform. The input to this one will be X. The output will be X reduced. This X reduced, it's the principal components. And in fact, we have a nice function here called the inverse transform. This inverse transform. I can use this inverse transform, in fact, to convert those X reduced one more time to X recovered, right? And plot the image. So we will do it. We can also open the code here, and after that, I will just plot it here. So I need to plot X, which is the original image, and the X recovered. Can we recover the same image? Can we still have the same information? We will compare. We will see. So this is the original set of images. Do you see this one? Each image here, it's a 28 times 28 pixel value, right? And now I will reconstruct the image again using only 144 principal components. 28 times 28, it's 78 what? I will so 28 times 28, it's 784, right? 784 pixel values. So in fact, each image here consists of 784 pixel. Now I will reconstruct it using 144, which means this image, in fact, it will be 12 times 12, correct? So now I reduce the dimension from 28 times 28 to 12 times 12, and I reconstructed the image one more time. When we reconstructed the image, I mean, we can still see it. So this one is still 5, this one is still 0, 4, but the resolution is much less because we do compression. So in reality now you are storing your image in 144 pixel values. If each pixel value is stored in maybe 3 bytes or one, imagine it's one byte. So it will be 144 bytes instead of 784 bytes. So now we can reduce also we can store it in less memory. We will need also less memory for storing it. We do compression, correct? So if you want to, if you want to send it, using any protocols, communication protocols, it will be much easier because it consumes less number of bytes, correct? So the memory will be much less. And it still carries the same information, right? So we reduced it from this one into this one, and we still can recognize that, okay, this one is 3, this one 3, this one 1, 4, 6, right? This one 2. So it's still possible. And also you can make this reduction to 8 times 8 or 6 times 6, for example, and you can see if you're still able to recognize it. So here we just need to define number of components. Those number of components does not have any meaning. Those X reduced, it does not have any meaning. You need to use this inverse transform to reconstruct the image one more time. And when we reconstruct the image using the reduced set, we still able to see that, okay, we can still able to recognize it because we used the maybe the first 144 principal components. But when we use principal component analysis, the input here was 784 inputs. The output also was 784 principal components, but we didn't use all those. We just selected the first 144 principal components and reconstructed the image one more time. So now if you want to build a model using 784, you can try it, you can test the accuracy, and again, you can repeat your modeling one more time. You can build a classifier using 144 inputs instead of 784. It will make huge reduction in the number of parameters, and maybe you will be able to get the same accuracy. Even if you couldn't get the same accuracy, but your model also will be similar. Maybe this model will have an accuracy of 99%, and it's okay. Maybe if you will train your model using the reduced set, maybe your accuracy will be 97%. It's okay. Who cares, right? It's a little bit less, but model building, I mean, when you are building your model, it was less challenging, right? It was much simpler to build a model with 144 principal components rather than using the full set of features. Yes. So now we can use this SGD classifier using 144 principal components, and we can compare. In fact, I don't know if I compared it with, yes. Yeah, I mean, we should, it will be nice if, in fact, if we can just compare. So now I'm building a classifier using 144. So instead of using X and Y, I mean, you will just use the reduced set, right? So it will be just the reduced set. Correct. I mean, why it's no problem. I mean, why it's the same. We don't care about why, because why are the labels, correct? So I mean, y train, y test, y train, y test, it will be the same, but we will just x train and x test, we will reduce, we will divide. We will replace x and y with x reduced and y reduced. This one now, it will be 144 column instead of using 784 column, right? So now we will use a reduced set. I mean, the problem here, if you want to test your model at any point, just remember that you are training your model with the principal component. So we need to have this principal component analysis because it will convert your features all time to get the reduced set. So if you are collecting data, right? If you have sensors and those sensors are collecting data, those collected data must go through the principal component because it will convert it into principal components. And we will send those principal components to my model for testing or inference, for example. So just remember that the input to your model will be the reduced set all time, not the original image. So you need to collect images. You need to send this image to the principal component analysis. And this principal component analysis, it will select 144 pixel values from this image. And we will use those 144 pixel values for, we will feed those 144 values to my model, not the original image. So this is the only disadvantage here. But in fact, now we are using a principal component analysis. Maybe in the next week, for example, we will use something else, which we will do the same, but it will be like a feed-forward model, and it will do also dimensional reduction using the same technique, but not principal component analysis. Yes. Okay. So, do you have any question for that part? Yes, I have also some comment from, would you? The price of a house, we could group features like number of bathrooms, number of bedrooms. Yes. Yeah, of course. Yeah, I mean, this is good example also. So someone here, he wrote a comment. So that if we are, I mean, try to predict house value or house price, for example. So the input features will be number of rooms, maybe locations, correct? Maybe age of house, maybe market value, correct? So there are many factors here. But if you will use principal component, so you will have only principal component 1, principal component 2. Principal component 1 and 2, for example, will not have any meaning. In fact, you cannot say that principal component 1 is price or is market value or number of bedrooms, correct? Number of maybe floors, age, maybe when the house was constructed, for example. So principal component 1, 2, and 3, it will be just principal component 1 and 2. It will not have any meaning, in fact. You cannot say that the first one is price. No, it's not price. It's not anything. And after training your model, now you are collecting data from the market and people will use your model. You need to use principal component all time to convert those real values into principal component 1 and 2. Yes, yeah, of course, there are many methods for doing this, Hisham. Yes, yes, okay. So what time is it now? Maybe you can take we can take maybe 5 minutes break, and after that we can take also one more slide, and after that we can go for presentations. Or should we start presentations after the break? And at the end, if we have time, we can cover another part. Is it okay?
Yes, it's
So
okay. Sounds
Yeah,
good.
okay. So we will take 10 minutes break. You can just get your coffee, and please maybe just it's voluntarily, so you can just anyone can just share his screen and they can start after 10 minutes. So I will stop sharing my screen so people can share their screens after the break. Thank you.
I just
Okay,
have a
thank you.
question.
Yes,
Ivan.
please.
This presentation that you're talking about, I don't, I haven't paid enough attention, obviously. What are them? Are they about?
Today?
Yes, today.
Yes. Yeah, it's about data pre-processing. So if you are working with features, for example,
No,
we
I was
can-
thinking the presentation that we are going to present in the group.
Yeah, it's a project presentation. If you have a project, because this course it requires working in a project. So just maybe one slide or two slides presenting your topic. What will be
Sure.
your research problem, which will be used in this course.
Yeah, sure.
Yeah, yeah.
Then I am prepared.
Yes. So if you prepared something, so can just people who are prepared something they can present. If you don't have something to present today, you can present it next time, for example.
Super.
Yeah. Thank you.
So I need to leave in 5 minutes because I have another meeting. Can I present the next week?
Yeah. No. Sure. Of course. No
Okay.
problem. Yes.
Great. Thank you.
Yeah. Thanks.
Yeah, for me as well. Is it okay if I do in the next meeting instead
Yeah.
of
Of
today?
course. Of course. We can just take people who are ready today. They can present.
All right.
And
Right.
when they finish, we will have another slide. So I will continue working after they finish.
All right. Okay. Thank
People
you.
who don't present this time, they can present next time. No
All
problem.
right. Thank you. Thank you so much.
Thanks.